Okay, so we have a model here where a population, okay, well, let's what is this? Changing growth factor. Decreasing growth factor in this case. Population starts out at 1 unit, as in the preceding, grows by factors of 3, then 2, then 1.5, then 1.2 in successive years. So we start with 1 unit of population at t equals 0. T equals 0 years. At t equals 1 year, population is grown by a factor of 3, which means you multiply 3 by the population at the beginning of that year, which is 1. You get 3 times 1 equals 3. That's the population at the end of your year. In the second year, the growth factor is only 2. So the growth rate is 2 for the second year. You multiply that by the population at the beginning of the second year here to get the population at the end of the second year. Then you multiply this by the growth rate for the third year. You get the population at the end of the third year. You multiply this by the growth rate at the end of the fourth year, and you get the population at the end of the fourth year. So these are calculations that anybody can do, arithmetic can do. Now, not everybody can do arithmetic, can think about the fact that the growth factor is decreasing. That doesn't mean that the population is decreasing. It means what you multiply the population by is decreasing. We see that the population triples in the first year, it doubles in the second year. Now, but it increased by more in the year when it doubled because it was starting with a greater population. So we see an increase of 3 here, we only had an increase of 2 here. Now the increase is, I've got it over here in a column, a delta P column. So we go from 1 to 3, delta P is 2, change in population. We go from 3 to 6, the change is 3. From 6 to 9, the change is 3. And then from 9 to 10.8, the change is 2.8. So we have increasing numbers when the population triples, but we didn't have enough population to start with to give us a big delta P. Doubling that significantly increased population gives us a population change of 3. And even though the rate is decreasing again, we get another population change of 3. But now the population is decreasing slowly enough that even though we've got a lot of population here, we don't have as big an increase. So you might want to think about that and think about those patterns. Doing the arithmetic is easy. Understanding the patterns is a little more challenging, but well within what people can do. Okay, so now here I have a graph of the populations. Populations are going up, they're continuing to go up. But if you draw a reasonable curve here, see the population goes up here, then it kind of goes up at a constant rate, and then it kind of starts to level off. Okay? Now there are many reasons this can happen. You might start to level off because you're approaching the carrying capacity of your environment. Okay? You've got a herd, it's only got so much land to graze on, it's, you know, mountains and canyons and maybe fences or something, and when you get too many animals, they don't have enough to eat, so the population starts to level off, giving you, incidentally, what's called a logistic curve. You got the carrying capacity of the environment, and you got the initial population. Population grows at a very high growth rate for a while, but then it starts leveling off and approaches the carrying capacity. Okay? Now over here, we've got a table of log of the population versus t, because the log graph is going to give you important information, especially when the populations change drastically. Okay, when you start with a population of 1 unit and end up with a population approaching 1 million units or 1 billion units. Okay, so t versus log p versus t. These are the approximate logs. I approximated these. Didn't go to a calculator or anything, but I think they're fairly accurate. Okay, you can see, I think they're all probably accurate within 100th or maybe 200ths. I graph the t versus log p. And my graph looks like this. The slopes decrease. Indicating decreasing. I'll abbreviate it like I did here, GF, for growth factor. From this graph, we can clearly see what's happening to the growth factor. It's harder to see what's happening to the growth factor on this graph. But as the growth factor approaches 1, it should be clear that you'd be multiplying 1 by the old population. You would get an unchanging population. You would be in this part of the curve, approaching stable population. Okay, well, there are interpretations of this sort of growth that are appropriate to the coronavirus, which is currently killing a lot of people and ravaging the world economy. It's a pandemic. It's really, whether you're seeing this today or 20 years from today, it's going to have had an effect. I'm afraid. I hope I'm wrong, but it's pretty clear. Okay, approaching 20% unemployment already. It's as bad as the Great Depression in that aspect. Hopefully not in other aspects. Okay, so if you started with 1 unit of diagnosed illnesses, and then after a certain period of time, like maybe after a week, the number has tripled, and that's apparently happened back in February and March, very fast growth rate. Then you start taking some precautions, and the growth rate drops to 2. And then drops to 1.5, then it drops to 1.2, and hopefully it goes into numbers less than 1, which will cause the population of infected people to decrease. Okay, so your population here would be the population of infected people, not the population of the world or the country or the state or the county, but the population of infected people in whatever region. Okay, so this is desirable, and you can see this happening before you're sure it is. Just look at this part of the curve. It looks like it might still be kind of exponential if you don't see this part. Okay, you don't see that it's kind of linearized here, and now it's starting to curve downward. You're still getting more sick people, but not as many more. And that's the stage we're clearly in right now. Now, hopefully with relaxing some of the rules, we don't go back into this type of curve. The log graph shows clearly the decreasing growth factor. Okay? The number over here is decreasing. And ideally, we'll reach a growth factor of 1 pretty soon. and we won't be getting more new cases, and the curve will start to decline if we don't screw it up. And don't ask me how to not screw it up. We have to weigh economic cost versus cost in illnesses and lives. And you hate to have to make those comparisons, but more lives get lost if the economy tanks too badly than would be lost to the virus. And it's just old people like me that are most of the victims. You got to be, you got to make these decisions. It's very difficult. Okay. But you do want to make the decisions based on what you know about epidemiology and what you know about things like this, because you can look. And if you're in my class right now, you're going to be assigned to look at these graphs. Okay? They have these graphs for every country in the world. And I think you have graphs for different states. You can see how the virus is progressing by looking at these graphs. And you don't necessarily know why it's progressing this way. You don't know what measures have caused this. And you don't know what measures that might be taken could allow the pattern to continue or screw it up. But it's worth looking at as an illustration of the importance of exponential and logarithmic growth. The other thing you want to look at is that if the growth rate stays at 3 per week, things really get out of hand very fast. Because this means that instead of doubling in the second year, you would triple in the second year, you get 9, and then you triple that and you get 27, you triple that and you get 81 instead of 10.8. Okay? And the graph would then look like this. And this applies not just to pandemics and so forth, this applies to populations in general. As long as you stay in the realm where things grow exponentially, in other words, you have a small herd and a huge area to grow in, and you'll tend to have exponential growth. That won't last forever in the real world, but you will have exponential growth. With a virus, you won't have exponential growth forever, because eventually so many people will have been infected and hopefully immune, with at least some immunity, that starts to suppress the virus, and not everybody gets sick. You can look at the forecasts and the numbers, and you can look at the way this unfolds over the next several months, even years. And understand it in terms of what you see here. Make your own guesses, see how you do. I'm not even making guesses. I just see the patterns as they emerge. Although I do expect, well, no, I'm not going to say what I expect. I have concerns both ways. I have concerns over too many people getting sick, but if too many people get sick, too many people aren't going to go to work, right? And that's going to tank the economy. So, ideally, we come up with some kind of treatment, some kind of vaccine, and some kind of balanced restrictions on people's activities to keep people from infecting each other at a high rate. And it all comes out on these graphs. Again, we don't necessarily know what the cause and effect is. We don't know if this kind of social distancing is what's causing this to happen, or if just people are staying away from each other spontaneously. We don't have the information, and especially we don't have the ability to do widespread testing, which would give us a whole lot more information. There we are.